An instrument for testing the soil density beneath a future highway. A control for sugar content in the making of applesauce. A way of determining the integrity of a boiler seam weld. An instrument to check the level in a can of beer. A tracer for reducing carbon deposit in gasoline engines. What do all of these have in common? They are among the many diverse applications of thousands of American companies which employ the safe, efficient use of one form of nuclear energy to produce better products. This is the story of the radioisotope safe, efficient service to industry. Here is a piece of uranium ore. To all senses, it is an inert and stable substance. Yet, with the proper instruments, we learn that this substance is constantly emitting energy. This phenomenon, this form of radiant energy, is the basis of an important new tool of industry, the radioisotope. To better understand the role of the radioisotope as a safe and reliable servant to industry, let us first explain the nature of this unique form of energy. The number of protons, or positively charged particles, in the nucleus of the atom determines the element. Though the number of neutrons may differ slightly from one atom to the next, its chemical properties remain the same. These different weight atoms of the same element are known as isotopes. Some isotopes are stable. They do not change spontaneously into other elements. Others, because of an imbalance in their nucleus, are unstable and eject particles or rays as they decay to a stable form. These emissions are called nuclear radiation, and the unstable atom a radioisotope. Radioisotopes emit three basic types of radiation. Alpha particles travel only a few inches in air. A sheet of paper will block them. Beta particles travel farther and are more penetrating, but they can be stopped by lightweight materials. Gamma rays are not particles, but a form of radiant energy, similar to light. They travel much farther and can be stopped by many dense materials. As seen here, different types of radiation at energy levels are obtained from different radioisotopes. While about 50 radioisotopes are found in nature, over 1,000 have been identified and made available. Man-made radioisotopes are produced by irradiating stable isotopes inside nuclear reactors. Approximately 100 such radioisotopes with a wide spectra of radiations, energies, and half-lives are now routinely made in this way. Within a chemical or compound system, radioisotopes act the same as their stable counterparts, except for the radiation they emit. These rays or particles, unlike heat or light, cannot be seen or felt, but they can be detected and accurately measured with sensitive instruments. Radioisotopes are excellent transmitters of information. Their radiations are able to penetrate substances of various densities and thicknesses in measurable amounts. The major use of radioisotopes in industry is in gauging applications. With over 6,000 radioisotope gauges in operation, they have proved to be industry's safest, most efficient instruments of quality control. Four major factors are responsible for the safe use of radioisotopes in industry. 1, low levels of radiation are often sufficient to do the job. 2, the safety features built into radioactive devices, including the sealed encapsulation of the sources. 3, the use of trained personnel wherever and whenever necessary. And 4, adherence to a few common sense safety procedures. In industrial use, the level of radiation necessary to do a particular job is usually comparatively low. Take, for example, this gauge used to measure the thickness of paper. The beta radiation emitted by the radioisotopic source is so low that it can be compared with the radiation given off by the luminous dial of a wristwatch. Adequate protection from low radiation levels is assured by the design and construction of equipment housing the sources. This typical radioisotope gauge contains many safety features aside from its ruggedness and reliability. The gauge is made tamper-proof by its locking device. Any attempt at tampering shuts down the system and activates an alarm. The hermetically sealed and well-shielded capsule is mounted in a carrier, which is brightly colored and marked as to its content. Many tests are conducted to study the effects of accidental damage to sealed radioisotope sources. Here we see a medical teletherapy unit being subjected to extensive trial-by-fire testing. Even after testing like this, there was no loss of radioactive material. Some radioisotope applications, radiography for example, require specially trained technicians. These men, specifically trained for radiography work, employ the same sort of simple protective measures long used for X-ray machines in industry and medicine. Radiographic exposures are made from behind protected areas. Posting and labeling are legal requirements of the United States Atomic Energy Commission, where specific quantities of radioactivity or radiation levels exist. Radiation areas are barricaded to permit only authorized personnel. Safety engineers in plants using radioisotope devices have found it to pose far less of a problem than certain other industrial equipment.
During the past 3 years that we've had nuclear gauges in operation in our plant, we haven't had an accident or stoppage because of them. From a safety standpoint, I'm sold on these devices, and so is everyone else here. None of our workers has the slightest anxiety about having radioisotopes in our plant.
The use of radioisotopes in our accurate gauges has not introduced any hazards in our operations. It has eliminated to a large extent the making of tear-outs to check basic weights. It has improved the quality of our paper and a reduction in scrap by keeping closer to the nominal basic weights. This scrap previously amounted to approximately 1,000 tons on our fine paper machines. Thanks to the availability of safe radioisotope material, it is now possible to control our papers with these systems.
To appreciate the safety and efficiency of radioisotopes in industry, let's briefly consider the application. A widespread industrial application of radioisotopes is in gauging systems. As shown here, an encapsulated radioisotope source is positioned opposite a detector. Materials interposed between them absorb or reduce the radiation from the source, depending upon the material's thickness and density. The amount of radiation reaching the detector can be read on a counter or meter. This information may be used to activate automatic controls and, in turn, regulate processing equipment. If the material is a mixture of inconsistent density, but of a constant thickness, the gauge indicates a variation in the density. With materials of constant density interposed, the gauge measures variations in thickness. Another setup measures the backscattered radiation from a material or surface. Now let's look at some of the practical uses of these applications. At a tire company, nylon cord is being carried into a calendar. Here it will be coated with rubber of uniform density to form sheets of tire ply material. As the sheets leave the calendar, they are constantly measured by two gauges set at positions of average sheet thickness. The gauge circuits actuate a continuous recording chart calibrated in pounds per square yard and automatically adjust the gaps between the rollers which control the amount of rubber fed. The results? Impressive material saving, as much as $15,000 annually by each installation, as sheet weight variations are reduced and held closer to optimum measurement. This is accomplished by gauges with a long history of safe use, responsible for uniform quality and a better, safer tire. Some important uses of radioisotope thickness gauges are evident in the steel industry, where they are employed for such processes as reduction of cold rolled strip, plating of tin on steel, galvanizing, sheet classifying. In each case, the thickness and type of material being worked with dictates the type of gauge used and the strength of its radioactive source. A gamma gauge is necessary when the measurement and control of thick steel plate is required. A beta gauge in processes involving thin sheet metals or plating. These gauges routinely control accuracy to within several millionths of an inch and effect tremendous saving on material and labor costs. They offer little or no hazard when compared to hazards associated with mechanical gauging methods, methods which include starting and stopping operations for such dangerous practices as cutting and sample weighing of hot sheet metals. An interesting use of the isotope gauge to determine density can be seen at this food plant, where applesauce is prepared and canned. An important determinant of applesauce's quality and flavor is its sugar content. The varying amount of sugar in each batch of sauce can be determined quickly and without sampling, simply by running it past a density gauge. The gauge reports the possibility of too much or too little sugar. It is so designed and located in the plant that it presents no hazard to workers. Extensive testing has proved that the minute amount of radiation from the radioisotope has no effect whatsoever on the food. This type of quality control is rapid, efficient, and highly accurate. At this Ohio brewery, each can of beer is automatically checked by a gauging system to make sure it contains the full amount. Those not properly filled are immediately rejected by a pneumatic system just beyond the gauge. Only full cans go out to the customers, and better beer too, because air in the can may impair flavor. At this refinery, level measurements of an entirely different scope are made with an isotope gauge. Within this thermal cracking tower, the level of hot turbulent fluid is measured by a radioisotope source in a well within the unit and a detector underneath. The fluid level is maintained at a depth of 3 or 4 feet on the basis of a gauge dial, which is accurate within a range of 4 inches. A gauge of this type also simplifies other difficult measurement problems. As they are located outside the tank, these fluid level gauges never come in contact with the fluid they are measuring. Therefore, service personnel never have to climb into a tank or other dangerous area to repair or adjust them. Here we see how a liquid level gauge works to automatically control the amount of fluid in the tank. It contains a small radiation source mounted on one side and a movable detector on the other. The flow valve is opened by the depletion of the fluid and closed when the desired level is reached. Other thickness and density gauges employing the reflection or backscattering technique are used to probe surfaces and report on conditions below them, such as this instrument which can indicate the density of soil beneath a potential airport runway or highway roadbed. These gauges are so well designed and their source so well encapsulated that by following a few simple instructions, workmen can use the instrument safely. A different type of isotope application is radiography. Isotope radiography units consist of a shielded housing for the stronger source and a means of unshielding the source for use. When the object to be radiographed is in position, with the film behind it, the source is unmasked. Film blackening is inversely proportional to ray absorption in the material and interior flaws. Voids or discontinuities appear as darker areas on the developed film. At this Tennessee plant, where pressure vessels, boiler tubes, and other components of conventional and nuclear power system are fabricated, radioisotope units have taken over a large portion of the radiographic work. To determine the integrity of girth seam welds on a boiler such as this, film is attached to the area to be inspected. Before the source is exposed, the specially trained radiographers operating this equipment go behind a protective barrier. From this area, they crank the source into its holder within the boiler. After a timed exposure, the source is returned safely to its housing. This is assured by a carefully metered survey of the well-posted radiation area. The radiographic film proves to any skeptical inspector the integrity of the weld. Here, as engaging the thickness and density of the materials to be radiographed determines the energy level of the source to be used. The portability of these units, the simplicity and safety of their use, the freedom from any high voltage current connection or cooling system saves time and money for those determined to turn out products without flaws or weaknesses. Because gamma rays are needed to penetrate heavier, thicker material, the levels of radiation are usually higher in radiographic work than in other applications of isotopes. Therefore, more exacting safety procedures are employed. Standard safety devices such as survey meters, dosimeters, and film badges, together with adherence to common sense rules, help to ensure accident-free operations. A third use of radioisotopes lies in the field of tracer applications, made possible because radioisotopes can be detected selectively and quickly, even in concentrations far below those levels permitted in ordinary drinking water. Tracer techniques are widely used in research and development, troubleshooting, and process control. The petroleum industry has pioneered many important research uses. At the laboratory of this progressive oil company, a piston ring, made radioactive by exposure to a neutron source, is fitted into a standard auto engine. After the engine is run for a period of time, its oil is analyzed by a counter. The amount of radioactive metal in it accurately measures the efficiency of the oil in reducing friction and wear. Tests of this nature permit the development of better lubricants and better engine designs. They are rapid and preclude the costly dismantling of engines for continued testing. Better fuels are also created through the use of isotopes. At this plant, various additives and elements in gasoline are labeled or tagged with radioisotopes. After running the engine, a careful analysis of the resulting carbon deposits on different parts clearly identifies what must be refined out of or added to the fuel in order to reduce troublesome carbon formation. Through the use of extremely low-level tracers, in proportions of less than a teaspoon to a tank load, it is possible to accurately separate shipments sent through hundreds of miles of pipeline. The injection of a small amount of tracer into the beginning of a shipment moves with it to a junction point. Here, at a point perhaps hundreds of miles from the origin of the shipment, an operator can determine its arrival as the tracer is picked up by a radiation detector. The minute amount of radioactive material of the tracer constitutes no hazard to the final product. Tracers can act as effective troubleshooters when a blockage occurs in a concealed piping system, such as the one lying under this floor. Radioisotopes serve industry in other ways. Because of the ionizing property of radiation, devices such as these can be used to control static. Radioisotope material is used in the manufacture of these luminescent safety signs, which will glow for years without the need of electricity. The signs are designed and constructed so as to offer no personnel hazard whatsoever. A long history of safe and efficient use of radioisotopes is primarily responsible for their expanding use in the applications we have reviewed, and for their adaptation to other industrial applications. This enviable performance record has made it possible for the AEC to issue a general license, thus sparing the user much of the paperwork previously involved in securing a license. The rigid safety requirements of the AEC are designed and engineered into the radioisotope devices. Their installation and servicing is conducted by radiologically trained servicemen, and plant personnel need no knowledge of radiation to operate them. From the radioisotope, this versatile source of energy and information, will continue to come many new and beneficial means of easing the productive burden of industry and of creating better products for America and the free world. Products which mean progress in this atomic age.